So Laura is going to come up. She likes the 1990 television shows. I know that for sure, because she was wearing a 1990s t-shirt yesterday, so, well, potentially it just means she likes those t-shirts.
Buffy the Vampire Slayer.
Feel free to come up, yes. Hello, Laura.
Hey! Fun fact about Laura. She started out studying social and cultural anthropology, and as you do, she ended up in tech.
That's what you do, yeah, because you need to pay rent somehow. And rent is getting expensive even in Berlin, unfortunately.
Well, so let's give it up for our final talk of the day. Laura.
Thank you. Thanks, I haven't even said anything of importance yet. So, my name's Laura, and I've been studying various things for the past 11 years, actually, and I'm still not done. But I've also helped organize Rails Girls Berlin for quite a while, and I would like to see everyone who's involved in Rails Girls or Rails Girls-like projects, either as a learner or as a coach or organizer, to raise their hands. Awesome. That's a lot of people, and thank you, because you're kind of, making sure this community keeps growing, and that's really important. So give yourself a round of applause. Okay, so now let's get this ship started. My references are not as good. Okay, so in 1998, Lauryn Hill released her debut album, The Miseducation of Lauryn Hill, and you might notice that this has something to do with the title today. So the title of her album is a reference to several other works, and they all make this point of how the US American school education system has been indoctrinating Black communities with white supremacy instead of teaching those communities and everyone else Black history and Black present. So the question of who educates and who produces knowledge is a question of who holds power over a seemingly universal truth. The Miseducation of Lauryn Hill is still one of my favorite albums today. And Kaya's. Right, and this title will guide us through the next 30 minutes, maybe also just 25 if I forget to breathe in between. So I want you to keep this in mind as we explore today how not just humans, but also machines gain and produce knowledge, meaning how machines learn. And I promise that I will leave out all the math, so you should all be able to follow. So let's take one more step back in time into 1950, where Alan Turing published a paper, and one of the questions he asked basically was whether machines can think. Now, thinking was really hard to define philosophically for Alan Turing, so what he did was not answer it and just tweak the question a little bit, and instead ask whether machines can imitate thinking. And this is something that you might have heard of as the imitation game, where we try to figure out if a human can actually make a difference or recognize a difference between interacting with another human or a machine. Now, for thinking, it seems to be hard, but for machine learning, we kind of have accepted this term. And I would like to question it, obviously. So spoilers, I will argue today that machines are not fully capable of learning, but really good at making us think that they are learning. And while it was hard for Turing to define what thinking means, I think it's a bit easier to define what learning means. And so I can actually prove my argument. For the purpose of this talk, I will understand learning as a process in 3 steps. And you might have noticed them in yourself, but I think also Melanie mentioned at least 2 of these steps today. And the first one is where you just learn to reproduce knowledge. It's like learning vocab when you're learning a new language. You need to get the terms right, same as in programming. And then you do the remixing part, and that was actually where we had the Pokemon characters created. That's remixing knowledge, taking knowledge from one domain and putting it onto another domain. And then the, final or most interesting level of acquiring knowledge actually is the reflection part, where you learn to understand where the limits of your knowledge are and what the knowledge can do and what it cannot do and what it should be doing and all of those things. We'll get into that later. So we will now look at 3 key elements that are involved in machine learning, and this is data, obviously, algorithms, obviously, and maybe as a surprise to people who don't know me, humans. And I will show you that data on its own cannot go beyond the level of reproduction, algorithms on their own cannot go beyond the level of remixing, and then humans cannot, well, we need the humans to do the reflection part. So now you know what this is all about. You may enjoy the sun. First, a quick content warning though. When we get to the last part of this talk, I want to give you an example of something that is hate speech, and it contains racism and sexual violence. So in writing, so I will not read it out loud. You can look at it or not look at it, but I will also let you know right before it comes up. So let's get started with the reproduction part of machine learning, or of knowledge, more like that. So machine learning is quite good at reproducing what we, as a human collective, already know. It can identify spam messages, it can make music recommendations, or translate from one language to another. And machine learning can also take that knowledge that we as a human collective have and make it available to a much larger set of individuals, right? However, machines can also learn the wrong thing. This is Caroline Sinders. I don't know if you've seen her talk at Republica this year, but she mentioned her music recommendation machine that put way too much focus on a few weeks of like breakup music that she was listening to very intensely, and that has screwed up her algorithm ever since, and Spotify is just suggesting Mumford & Sons all the time. Now, I don't have a great taste of music, so I'm not judging that at all. But the only option for her is actually to delete her account, create a new one, and stay away from that band forever, because she cannot get rid of them otherwise. That was the fun part, but there are also plenty more serious examples where reproducing human behavior is not really a good idea. So you might have heard of some of these cases, because machines are really good at learning bias. They apply bias in recruiting tools, such as one that Amazon once built. They apply bias in the justice, or, well, rather the injustice system. And they apply bias in image classification. Because humans do bias quite well, it will be found in most data sets, and thus machines learn to reproduce it. But it's also more than that. So the artist Hito Steyerl puts it this way: those who own past data colonize the future. And what that means is that machine learning predicts the future based on past data. So we always use the past in order to learn or predict something in the future. So whatever has been will always be taken into the future. So that's hopefully our first learning for today. Data as one element of machine learning will not learn beyond that level of reproduction. How about the next step of learning? Remixing. And I don't mean like the scratching DJ thing. Well, before we can continue this talk, I need to know whether you are human. And I'm asking you to please select all the images with a bike. And since I have no proper interface for this, we have to agree on something. And I have a suggestion, and I hope you're all down for this. So does everyone know what jazz hands are? It's like you're wiggling your fingers, and you can do it up here, or you can do something similar, whatever feels okay for you. So I'm going to show you 4 images. And when you identify a bike, please give me your best jazz hands or spirit fingers. And if not, just don't move. OK. So does this image contain a bike? Does this image contain a bike? Did someone bring their bike and it's secretly hidden in there? Does this image contain a bike? And does this image contain a bike? Okay. This also contains some Rotterdam architecture that you might want to check out after this talk, because it's really awesome, those cube houses. So, congratulations. You're not a robot. However, or you just tricked us really well. However, I was the one asking the questions, so we still don't know if I am. So let's pretend that I actually am a machine, and you classified some bikes for me, and so obviously now I'm going to learn how to classify bikes, because that's what I was built for. And I'm gonna start doing so by first simplifying this image a little bit, because I am not the most resourceful machine, and this has a really good resolution. And I'm gonna lower the resolution and drop the colors, and this has now like the size of my pants for resolution. It's still way too much. I'm gonna lower the resolution even more. Can you still identify something? You know what it should be, so you can, right? Okay. So I will start comparing this image with very basic shapes, like horizontal lines and vertical lines. You've seen these in your life before. So I'm going to use these in order to identify parts of the bike that are standing out. And I'm going to start small with just these shapes, and it's going to get more complex, but I didn't draw more of these. So you as humans, you can already identify some of these shapes in the image, right? If I walk around here and you can like tell me which shape is where, does someone have an idea? You can just yell at me. This one on the bottom left? This one? Oh, yes. And look, I even measured, and it's the same pixel size. Also, I think thanks to Melanie, because she gave me a ruler. Right, so you as humans, you can like identify that this is a horizontal line. You might also be able to identify that over here is a vertical line, right? Yeah, but me as a machine, I cannot. What do I need to do? I need to do numbers, yes, but I promised to leave out all the math. So what I would do is I would take one shape and I would start at the very top and put it on there and see if what I have is similar to that part of the image. And then I would move on 1 or 2 pixels and compare again. And then I would move on 1 or 2 pixels, and you know how machines work. What would I do then? Move on. Exactly. And I would do this for the entire image. And then I would use this other one and do that for the entire image. And while I'm doing this, I'm actually still not really identifying shapes. I'm just redrawing the image and creating a new one. So I create a new image that's based on the old image and the shapes that I have. And so if I apply this one, my final image, if I apply this one, my image that comes out of the comparison is going to look something like this. You as a human can maybe not see much more in it. And if I apply the horizontal filter, it's going to look something like that. And so I'm going to do this with other shapes as well, and I'm going to take these new images and apply combinations of shapes and so on, and this will continue to reduce the size as well. And the images will get more and more abstract and smaller, and you as a human will no longer be able to recognize. And once I'm done with one image, I'm going to do that with all the other images that you that you classified for me. So these are all from the ones that you handed out for me. And then I will remember the quintessence of them. And I will end up with some blobs that you definitely can no longer recognize. But I, as a machine, can now use them. And this is basically the intuition for a convolutional neural network. If you've never heard of it, there you go. So what I do is I extract different shapes from images that are defining for the shape of a bike. And then I end up with knowledge, and this can now help me to determine which shape is how important in a bike. And once I have these abstract ideas, you can hand me a new image, and I can tell you whether this contains a bike or not. This one does not contain a bike, but it is Mats holding like my name at the airport. So I needed to include this somehow. But you could also hand me this image, and I could probably say this might very well include the image of a bike. However, there are some problems to this example, to this approach, and I want to show you one example. There was a study last year, actually, that tried to trick machines like me. And I believe that those researchers had a lot of fun doing so, because what is this? Yes! So their classifier actually classified this as a bike. Because the elements, or from a machine perspective rather, the basic shapes of a bike exist, right? They're present. And it doesn't matter that in this setup the image makes no sense to a human and the bike, well, is kind of broken. But this shows us how machines tend to overlook the bigger picture. They can mainly just look at images as a combination of shapes, but they fail to see them as a whole most of the time. So second learning for today. Algorithms, as another element of machine learning, do quite all right at reproducing. They can extract and reproduce shapes and see if other images are similar in that respect. And quite literally, this machine does well with remixing images. But remixing, of course, does have a different meaning too. So when we come to the context of so-called transfer learning, algorithms can use knowledge from one context that they have learned in one context and apply it to a different context, but this is still in the making, kind of. So however, algorithms do struggle with like the bigger picture, and this gets us to the third part, and a drink of water. So reflection. Imagine that I had asked you to do a very different task. Imagine I had asked you to identify hate speech. So while detecting objects such as bikes is rather easy, speech is much more complex, as we've also heard today. And within speech, hate speech is even more complex. So I'm currently assisting in a research project that aims to analyze hateful communication on social media and commentary sections of German news media in order to identify causes and dynamics of hate speech. So we're looking at comment sections of German news media on the topic of migration. So you can imagine that there's a lot of terrible things going on. And we're trying to actually develop methods and software that can recognize hate speech early and that can also suggest strategies for de-escalation. So everyone who was going like, freedom of speech, it's about de-escalation, it's not about deleting. So let me tell you, finding hate speech is a lot harder than finding bikes. And unlike many other projects that try to do that, we involve both communication science and computer science, and they kind of work together in this project. So I will show you how each of these perspectives try to learn hate speech. Let's get started with the computer science part, because this might be close to what you already know. So to identify hate speech, machines do what we call supervised learning, right? Some of you know this, have heard of the word. Okay. So what happens in supervised learning is that we take a set of data that already has the information on whether a particular statement is hate speech or not. And then we split it into two sets, and you can only see the train set here right now. One is for training and the other one is for testing. And so the training begins. And this is actually where that training part can also be done with convolutional neural networks. So we can use our knowledge from the bike part for identifying hate speech as well. So unfortunately, text only works in one dimension, and this is 2 dimensions. So text either goes horizontal, right, or it goes down. And this English text only goes from left to right. So we're not comparing our text to shapes particularly, but rather to positions. So I promise to leave out all the math, but you can imagine that each word in our entire data set, which is bigger than this one, has some kind of relation or position within the text. And now instead of looking for horizontal or vertical lines like we had before, we will look at how words or even characters relate to each other. So the size of these relations can vary. We can look at the character level. We can look at how two or three characters relate to each other, or as you can see here, how two words can be related to each other. And then we move our two-word filter over our text, like this and that. And next we could choose a differently sized filter that, for example, looks at 3 words, and so on. And eventually we will have numbers that I did not include, that show what kind of words have what kind of relation within hate speech statements, as opposed to what kind of words have what kinds of relations in non-hate speech statements, according to the different filters that we apply. And so instead of having a byte classifier, we might now have a classifier for hate speech. And in order to check how good that classifier actually is, we're going to use the second part of our data set, the test data set, and we will check how well our classifier can tell hate speech from non-hate speech. And since we humans already know from our data set whether a statement is hate speech or not, we know what the machine should decide, so we can compare what it should decide to what it actually decided. But usually the result is not very satisfying, especially not in the beginning. So we need to go back to the training part and, well, actually adjust numbers. We tweak some numbers here and there, and if you're looking for a scientific explanation, I cannot give you one because most of the articles just say, adjust parameter X or Y until it looks good. Thanks, science. And so we do this until we're satisfied with our results, and then we can calculate some measures for quality and end up, for example, with a classifier that will give us a green light for probably not hate speech, or a yellow light for, I don't know, could be not, and then a red light for, yeah, this is probably hate speech. Sounds good so far, but where do machines fail? Well, unfortunately, machines cannot tell us themselves where they fail. Not in this case, at least. So luckily, there are humans who don't take machine results for the truth, and they question them thoroughly. And this is a paper that was published within the project that I work for. And to test the waters, they took a huge Wikipedia dataset and one from Twitter, and both of them were tagged not for hate speech, but for toxicity. But I want to give you one example. This is not the content warning. This is just an example. Oh, I feel like such an asshole now. Sorry, bud. This was tagged by the algorithm as toxic. Well, because based on the training data that the classifier received, it very strongly learned that swear words are an indicator for hate speech. Well, in this case, it's actually someone apologizing for their behavior, I would guess. So statements that include swear words but do not actually attack someone are apparently hard for machines. There are other things as well. Hate speech that, on the other hand, does not contain swear words is difficult for machines to identify. Rhetorical questions are hard, metaphors and comparisons, idiosyncratic and rare words, sarcasm and irony, quotations or references. So if you relate to someone else's statement and point out that their statement was not okay, but you're using similar language, that might also be flagged as hate speech. So not really optimal, because all of these things are used a lot in those statements. And that's because the algorithm is so focused on the words themselves, and it cannot look beyond the text that it has been given, right? It has no context for the actual meaning of words and how this changes within different contexts. But we kind of skipped the part about the underlying data set on which machines learn. Those data sets don't just appear, obviously, they're created by humans. So how do humans learn to identify hate speech? Very often, these data sets are created by crowd workers. Has anyone ever been a crowd worker for any task? Okay, 1 person, 2 people? Okay, thanks for doing that. So for the Google Perspective API, for example, rather random people were simply asked to rate an internet comment on a scale from very toxic to very healthy. Now, unfortunately, results from crowd workers are kind of unreliable, and their results also won't really explain to us why they made a specific decision, right? They just click and then we have the result, but no context. So it's okay to do that for bikes, because most of the time it's not so bad if you misidentify a bike. But for hate speech, it's a different thing. So social sciences and communication studies in particular, they go about this a bit differently. Our strategy is usually to start with, well, some theory. And let's define what hate speech actually is. I have brought you one example of a definition, and it goes like this. Hate speech is understood as public communication that contains deliberately and/or intentionally discriminatory messages. Thus, it is not a question of hate, nor a question of speech. Are you confused? A little bit. I think this is a very good definition, because it points out that hate speech is not about an individual's emotion, or about emotions at all, really. And it's also not limited to speech, because hate can be expressed in many ways, and it can appear in rather rational ways. But we still need a way to identify this. So we're going to agree on this definition for now. And once we have it, we have to actually see how it applies on specific statements. So we need to take the theory into like the methodology. So according to our definition, we could take public user comments, then we have the public communication, and say that verbal aggression, so things like insults, negative comparisons or metaphors, negative circumscriptions, are hate speech. Dehumanization, meaning turning humans into objects or creatures, is hate speech. Calling for threatening or legitimizing violence against people is hate speech. And negative generalizations, such as all X are something terrible, is hate speech. Now, we will take these practical understandings and put them into a code book. It's kind of a tutorial on how to find hate speech, and it contains the definition that you've just seen and the more practical understandings, but also lots and lots of examples and context. And so what we do in our project is we give this codebook to humans, but not as many as the crowd workers, rather to a smaller number, like 3 to 7 people maybe. And they're called coders. And they read this book, and then in a workshop together with the researchers, they discuss a lot of examples and they work together on them. And then they take even more examples and the codebook home and like rack their brain on these examples and meet again to discuss all of their questions, because this is where a lot of questions come up. And I want to now show you an example why it's important to discuss all of the questions, to first of all have questions and then discuss them and come to a decision on them. And so now, this is the content warning for racism and sexual violence in words. It's going to be on the next 2 slides. I'll let you know when they're over. This is a translation of a comment that was originally in German, and I translated it by words, basically, for now. So you may not understand what this is supposed to mean. Does anyone, like, kind of understand what it means? Okay. Because the language is really coded. It's using references to words or phrases that, well, German politicians have made in the context of migration. But it's also turning them around, and it's really weird sentence. So unless you're quite familiar with this topic within the German context, you'd probably be rather unsure whether this is hate speech or not, or you might just dismiss the comment, right? I can tell you that we actually find 3 indicators of hate speech within this very short statement. It's legitimizing violence, that's this part. It's also making an ironic and negative generalization, that's the second part. And then there's a third part that is turning humans into objects again, with a note of sarcasm. Now keep this in mind, and I will show you the translation by idea. So this is translated again, but what it actually means. So I think you now understand why this is hate speech, after all that we've been through. And that's it for the content warning. So once the coders have asked and discussed all their questions, we usually need to add better descriptions and examples into the codebook. And this is such an important step that this could actually go on for 1 or 2 more rounds, right? And then eventually the researchers are confident in the coders and their calculated agreement is high enough, and they will actually code a larger data set, and that is then where the algorithm can start to learn. But where do humans fail? Well, no matter how good the discussions and the trainings are, a data set will never be perfect, because humans too have trouble understanding irony or sarcasm. Duh. But more importantly, language and specific words can change over time, and sometimes their meaning can change quite quickly. However, we as humans have the capability to pay attention to this, and that is now of the uttermost importance. Because humans are the ones who can stop, take a step back, and look at the bigger picture. Humans are the ones who actually complete the entire process in machine learning. We are the ones who educate or miseducate the machine. So I would like to finish up with a quote from Lauryn Hill's album now. "Consequence is no coincidence, because the knowledge that machine learning produces is no coincidence. It is a consequence of what data we as humans choose to feed to a machine. It is a consequence of how we as humans build an algorithm. And finally, machine learning is a consequence of what we as humans decide to question, reflect upon, or take with a grain of salt." So all that I'm asking you now, whether you program machines that learn, or you use them, is to please be the human that reflects. Thank you.
Thank you so much, Laura. Little something from us.
Thank you.
Thank you. That was an incredible way to end the day, huh, folks?